Alright, welcome to Algebra 2, Unit 6, Section 5, Location Principle and Multiplicity. After this lesson, you should be able to determine the location of a zero from surrounding x values and apply the concept of multiplicity to the zeros of a graph. Okay, this is the third time I'm recording this video because the first one had some technical difficulties. The second one had some audio issues, so now we're trying it a third time. Hopefully this one comes out. So what is a real zero? A real zero is nothing more than the x values of a graph when it touches, let's spell it right, touches or crosses the x-axis. Okay, so those are the real zeros. Distinct zeros are the separate x values of zeros of a graph that are different. They're not the same values. Okay, so once we find a zero, how do we know if the graph is increasing or decreasing? Well, some of these things can be done by using what's called the location principle. And if a value of a polynomial f of x changes signs between x equal to a and x equal to b, the function must have a zero somewhere between a and b. Okay, so let's take a look at these two, or not these two, but at this graph here. I have this line, and this function would be f of x. It's in slope-intercept form, so its slope is 1 and its y-intercept is -2, so x minus 2. And we can see that the graph hits the x-axis right here at 2, so at 2, right? And we can plug values in to the function from 1 to 3, and we'd see at f of x, x equal to 1, f of x would be equal to -1. X equal to 2, x is equal to 0, or f of x is equal to 0, and at x equal to 3, f of x would equal +1. So what happens between 1 and 3? Well, the function changes signs. Right? It changes from negative to positive. So what this does is it tells us there is a zero somewhere between when x is equal to 1 and x is equal to 3. And there is at x equal to 2. So what we can do is we can take other functions and plug in, and then we know we can discuss what's going on with those functions. So just plugging x equal to -2, 3 times -2, -6, minus 3 is -9. 3 times 0 is 0, minus 3 is -3. 3 times 2 is 6, minus 3 is +3. And 3 times 4 is 12, minus 3 is 9. So we can look here and we can see that between the values of 0 and 2, this function changed values or signs from negative to positive. So we would state that the 0 is somewhere between 0 and 2. And that's how we write it in the interval notation. This next function we're going to take a look at, and I'm going to put a little note over here that 1 is equal to 2 over 2, because this is going to make my algebra a little bit quicker. So negative 3 times negative 1/2 is positive 3 halves. Positive 3 halves minus 2 halves, right? 1 is equal to 2 halves. Positive 3 halves minus 2 halves is positive 1/2. All right, negative 1 times 1/2 is positive 1/2 minus 2 halves is negative 1/2. 1 times negative 1/2 is negative 1/2 minus 2 halves is negative 3 halves, and 3 times negative 1/2 is negative 3 halves minus 2 halves is negative 5 halves. So again, we can see here that between these two values of x here, these changed signs. So this means that the 0 is somewhere between negative 3 and negative 1. And this is perfectly okay in the world of higher mathematics. Where's the 0? It's somewhere between 0 and 2. We're fine with that, unless we can solve for it exactly. And we'll see this later on in one of the problems that we'll be working on. Okay, so now that we know the location principle, we're going to apply this knowledge about zeros to determine what happens at the x-axis for each 0. So we're going to factor this function. So f of x is equal to x squared minus 1. And when I factor this, it's a difference of 2 squares. So I'm going to end up with x plus 1 and x minus 1. The square root of 1 is 1. Square root of x squared is x. So that's how we factor that very quickly. Okay, the zeros. Well, if we take this and we say x plus 1 equals 0, and then we subtract 1 from each side, so x is equal to negative 1. X minus 1 is equal to 0. Add 1 to each side, we get x is equal to positive 1. So one of the things I'd like you to take a look at here is that we have this situation here. It's very easy to find these zeros here when we have a coefficient of 1 with x. We just have to change the sign, right? Over here it's positive 1 to the left, right? X plus 1 becomes x minus 1. X minus 1 becomes x equal to 1. So my zeros here are negative 1 and 1. And my degree is always the highest exponent in the function, so in this case the degree of 2. So we're going to go ahead and plot these zeros. My y-intercept is negative 1, right? It's always going to be the constant value. And once we take a look here, if I plug negative 2 in, negative 2 squared is 4. 4 minus 1 is 3. So I'm going to put this here. And same is true of 2 squared. I'm going to end up with this. So we end up with this parabola. And we've done these for quite a while now in class, where we are graphing these as such. Okay. Now the thing that's interesting is over here I am positive. All my values are positive f of x values. Alright. And then I hit negative 1, and then this all in this area here is all negative. And then we come back over here and it's positive again. Okay, so we can tell that for certain areas of x values we're going to be positive or negative. So let's take a look at another one here. of f of x equals x cubed minus 2x squared minus 25x plus 50. Okay, so we're going to factor this, and we're going to do it by grouping. So I'm going to group these two, and I'm going to group these two. And I'm going to get g of x is equal to, my greatest common factor between those two is x squared, and this is going to be x minus 2. And it's negative 25 here, so minus 25, and it's going to be x minus 2 again. And we've talked about this when we factor these. When we factor by grouping, these two must be identical. So we're going to end up with g of x is equal to x squared minus 25 times x minus 2. And again, we have a difference of 2 squares in the first binomial there. So I'm going to factor that quickly. So perfect squares, x plus 5, and x minus 5, and then x minus 2. So we're going to put all this down here. And my zeros are at negative 5, positive 5, and then positive 2. And my degree is 3, right? Because right here is our degree. Okay. Now, a couple of other things that'll help us out. I know my lead coefficient here is positive 1. So that's going to have an effect on this as I start to graph things. So the first thing we're going to do, you come and you graph your zeros. So I've got negative 5, and I got 5 over here, and then I've got 2. Okay, next, I'm going to graph my y-intercept, right? The y-intercept was, let's move that over here. The y-intercept is right there. Okay, so that's going to be 50, so I'm going to put that up here. Okay. Now, a couple of things I know, because my lead coefficient is 1, that this function is going to be moving, this is going to become more negative on this side of the graph. So I'm going to be coming down here, and this side of this graph is going to be coming up here. So now, let's assume that we're going to somewhat be balanced here with this, and we're going to be balanced here with this, and it should look something like this. Now, one of our tools that we can use is a graphing calculator. So we're going to go ahead and use that, and we're going to plot this equation, right? This function. So I'm going to put in x cubed minus 2x squared minus 25x plus 50. And we're going to make some adjustments to our window here, because if you take a look at this window, all right, this graph goes from negative 7 to positive 7 for x values on a scale of 1. But my y minimum is at negative 40, and my y maximum on this is 60, and my y scale is 10. So I'm going to graph this now, and we go way higher than what we did on this graph. Okay, so let's adjust our window. So let's go up to 90 for our y max. and let's graph it again. And there we go. We've got a nice cubic polynomial graph. So I'm going to put this here right next to that to compare and contrast. And we can see here that our graph is pretty close. It's not perfect. Okay, we did sketch it, and that's all we're trying to do is get a good sketch. Okay. All right, let's take a look here at our another graph, but this one's a little different in that it's already factored. So we've got p of x equals x minus 3x plus 2. So our zeros are going to be 3, 3, and negative 2. So this is a third degree polynomial. Right? So let's talk about now graphing this. Well, I need to put a 0 at negative 2 and another one at positive 3. My intercept for y is at negative 18. Okay, so let's talk about what happens next. Okay, I've only got 2 zeros here. Well, I know that from this 0, it's going to go down. And this 0 here is going to travel upwards. Okay? I'm going to make that a little bit thinner, let's say. Like so. Okay. So what happens, right? So when I have two non-distinct zeros, right? I have 2 zeros at 3, right? But they're not distinct. Okay, so what we see here is, and I'm going to guess that this is going to go up and then come back down like so. That's what I'm thinking it's going to do. Alright, so there's my rendition. Let's see what we do with the graphing calculator. So I come back over here, and again, this is, we'll clear this out, and we're going to say x cubed minus 4x squared minus 3x plus 18. And I got to fix my window. The x values are fine. My y minimum is negative 6, and my y maximum on this one is 20. And our scale is by every 2. That's what, according to what our graph on paper is doing. So let's go ahead and graph it. Okay, so this graph is actually, I'm off a little bit, right? But you can see here we've got a fairly close drawing with behavior, right? This graph here should have come through here and then up and then down. Okay? And I'm a little bit sharper looking than you know, probably should have been. Alright, so what do we notice? Well, this one went through the 0, but this other 0, it touched it and went back up. Okay, which leads us to what we call multiplicity. Okay, so multiplicity is basically the number of times a factor slash 0 occurs in a function graph. And the reason I say graph, because that's important, in parentheses. Alright, so we have a couple of different things here. 3 types that we're going to talk about. The first one is a cross. Basically what you have is this is with a multiplicity of 1. Alright, and the graph travels through. Okay, so it changes signs, right? It either goes from positive to negative or negative to positive. So an example would be something like if we have like x plus 1, x minus 1, x plus 2. Each one of those factors only occurs one time. They're all distinct. Okay? On a bounce, you have even values of multiplicity. So that would be like, something like this. If I had x minus 2 squared, x minus 3 to the 4th. Those both have even multiplicity. Okay, it's going to bounce off of the x-axis. A slash has odd values. And greater than 1, right? So would look something like this: x plus 3 cubed, x minus 5 to the 5th, right? Those multiplicities each have odd valued exponents. Okay, so this passes through also. This is a pass through also, but it does it in a certain way. All right, it gets very flat, or like 45-degree angle or less. Okay, so let's take a look at some graphs and we'll be able to see what this is. So over here I have some graphs. Okay, and we're going to take these graphs and look at all these issues. Alright, so the first thing we want to do is look at the total number of zeros. Well, one thing that helps is to figure out what's the degree. Well, so we talked about, we have these valleys. Here's a peak and here's a valley. So this would be a 4th degree polynomial. So if it's a 4th degree polynomial, it has 4 zeros. Now we have a 0 here, there's 1, here's 2, and here's 3. So it only has 3 distinct zeros. So now we take a look at these zeros. Okay, so I have a location here of -3, -1, +3. Well, at -3, we're positive here, but then we hit this area here, and it's negative under this, right, from here to here. Okay? So because of that, that is a passing through, that's a multiplicity of 1. So at negative 3, I'm a 1. At positive 3, I'm also a 1. Well, the only remaining 0 is negative 1. And you'll see here what happens is I don't change signs. I become negative at this point here, right? I'm negative here. I continue up to here, and then I go back to negative. I stay negative. All right, I don't change signs after hitting 0. Okay? So, because of that, this multiplicity is 2. Okay? This next one, we have a peak here, we have a valley, we have a peak here, we have another valley. So there's 4 peaks and valleys, which means that's a 5th degree polynomial. So that means I got 5 total zeros. And in fact, I do have 1, 2, 3, 4, and 5 distinct zeros. So since all of my zeros are distinct, they all have the same multiplicity, which is, watch this. So my locations at negative 2, negative 1, 0. Let me move this over here. 1 and 2, but it has all the same multiplicity of 1. Okay? So that's 2 examples there. Okay, but now let's look at some more. All right. Given a polynomial of degree 6. Well, they're telling us the number of the degrees, so they're telling us there should be 6 zeros. But I'm only seeing a 0 here, and I've got a 0 right in the middle of this. So there's only 2 distinct zeros, right? Negative 2 and positive 2. Now, the multiplicity of this. How do we figure this out? Well, since this is a bounce here at negative 2, but it's thin, it's very, it's not flattened. It's rather sharp. That's going to have a multiplicity of 2. And at 2, this is going to have a multiplicity of 4. Okay? So given a polynomial of degree 7, how many zeros? Well, again, it's going to be 7 zeros. But I only have 2 zeros. I've got one here at negative 1 and one at positive 1. So at negative 1 and up here to positive 1. So my multiplicity at positive 1 is 2. It's got to be even, right? Because it's bounce. At negative 1, this is what we would consider a slash. It's flattened here, right? It's very flat. So we would say the multiplicity of this is 5. And the kind of neat thing we can do, you can actually take your graphing calculator here and build this function without even knowing anything other than this. I can say, all right, so if the 0 is negative 1, this is x plus 1, and I'm going to make it go up to the 5th power. And my other 0 is x minus 1, right? And I'm going to square that. Let's fix our window. We'll go from negative 2 to positive 2, and we'll go from -1 here, and we'll go up to 2, +2, and we'll do a scale of 1. And we'll go ahead and we'll graph it. There you go. This graph is pretty much identical to the one we were originally given. So you can recreate these using the graphing calculator. Okay. So our final piece of the puzzle here. In this graph here on the left, the one in green, I have no zeros, right, that are visible. But I do have a valley here, a peak here, and a valley here. So this is a 4th degree polynomial, but it doesn't have any zeros. We never come on down and make contact with the x-axis right here, right? We never make contact. So, does it have zeros? And the answer is yes. It has 4 zeros. Number of distinct zeros. This is unknown. What's the location? We don't know. Okay, do we? Or do? Yes, we do. These are what's called complex. So you'll write complex. This means that there are values that make the discriminant negative. So I is the square root of -1 is part of these answers. Okay, they're complex numbers. If you remember, that it's in the form of this: a plus bi. All right, and this multiplicity we don't know. So those are your answers for this type of problem. Okay. This problem here is pretty simple, right? It's got a peak and a valley, so it's a 3rd degree polynomial. So it's going to have 3 zeros. And we have 3 distinct zeros. We got 1 here, we got 1 here, and we have 1 here. Now, here's the situation though. Let's take a look at our distinct zeros is 3. So we have 1 at -5 with a multiplicity of 1. I have another one at +4 with a multiplicity of 1. And I have a third one here that I don't know. I don't know what that is. I don't know what that value is in there. So how do we express this? We would say the location is between 1 and 2. We do know the multiplicity is 1. Now, you might be thinking to yourself, well, wait a minute. That's okay just to tell about where it's located and not to have to solve this. Perfectly acceptable. I don't know exactly what it is, but I know where it's located. I don't know its exact location, but I know approximately where it's located. Is completely acceptable in higher order mathematics. So that might be a little bit new to you, that this is okay. And it might be a little disconcerting or uncomfortable, and that's fine too. Okay? So, that's the end of our lesson for today. We got through this one. So, have a great day. Peace.